Section: Introduction. In this section, we explore recent advancements in large language models, LLMs, and their reasoning capabilities due to increased scale. We aim to understand the sensitivity of LLMs to layer deletion and swapping during inference. Our study reveals 4 key stages of inference: detokenization, feature engineering, prediction ensembling, and residual sharpening. We build on the idea of iterative inference, where each layer updates token representations gradually to improve predictions. Networks show self-repair and redundancy, supporting this iterative process. However, there is also specialization in networks, with specific roles for attention heads and neurons forming complex circuits. We investigate the robustness of language models by deleting or swapping layers and analyze the roles of different depths in the network. Our experiments identify 4 phases in the model: detokenization, feature engineering, prediction ensembling, and residual sharpening. These phases show how the model processes tokens from raw representations to specific predictions. Our framework sheds light on the intricate token processing in advanced language models. In the realm of interpretability, research focuses on circuit analysis to understand model components for computations. Studies in computer vision and language models reveal universal mechanisms like induction heads and knowledge neurons. Depth-dependent studies, such as the logit lens technique, explore how models update hidden states across layers. Iterative inference is crucial in understanding how models make predictions. Recent works highlight the importance of specific layers in large language models and suggest an order to computation. Our study contributes to this ongoing exploration of the inner workings of language models. Section Summary. In this section, we explore the sensitivity of large language models, LLMs, to layer deletions and swaps during inference, identifying 4 universal stages: detokenization, feature engineering, prediction ensembling, and residual sharpening. Our experiments reveal the importance of different depths in the network, showcasing phases like detokenization integrating local context, feature engineering building representations, prediction ensembling emphasizing relevant predictions, and residual sharpening transitioning to specific next token predictions. This framework sheds light on the intricate token processing in advanced language models, aligning with previous depth-related findings within interpretability and suggesting a preferential order to computation. Section: Robustness, quantization, pruning, redundancy. In this section, we have explored the robustness of language models through quantization, pruning, and redundancy. Previous studies have shown that pruning or quantizing models can reveal depth-related insights. While most research on zero ablations of transformers has focused on BERT-style models, similar principles can apply to other models. For instance, removing the final layers of a model can maintain its performance, and studies have indicated significant neuron redundancy in BERT transformers. In terms of model quantization, keeping only the low-rank components of certain parts of the models has shown improved benchmark performance. Additionally, analyzing token frequency dependencies in MLP weights has provided valuable insights. The relationship between robustness and token frequency suggests that pre-training data plays a role in enhancing robustness. To investigate the inference stages in language models, we have studied the Pythia, GPT-2, and Microsoft Phi model families, which vary in parameters from 124M to 6.9B. Despite architectural differences, these models exhibit consistent inference patterns. We have evaluated them on a dataset to ensure a fair comparison and minimize the impact of domain shifts. By conducting layer swap interventions and ablations, we have gained insights into the importance of different model components at various depths. Swapping adjacent layers has been found to be less harmful than ablating layers, indicating that certain operations in the forward pass are commutative. Our results suggest that GPT-2 models are more robust than Pythia models due to factors like dropout during training and the number of parameters per layer. Overall, our interventions have shown that the first and last layers play crucial roles in model performance, while middle layers are more resilient to changes. Further experimentation is needed to fully understand the impact of different interventions on model behavior. Section Summary. In this section, we explore the robustness of language models through interventions like quantization, pruning, and redundancy analysis. By studying the behavior of different model components at various depths using layer swapping and ablation techniques, we find that intervening on the first and last layers significantly impacts model performance, while middle layers exhibit robustness to changes. Our results suggest that certain operations within the model's forward pass are commutative, with GPT-2 models showing greater robustness possibly due to dropout during training and fewer parameters per layer compared to Pythia models. Section. Why are language models robust to layer-wise interventions? In this section, we explore why language models are robust to layer-wise interventions. We believe that this robustness is partly due to the presence of residual connections in the transformer architecture, which increase redundancy. While skip connections were initially introduced to address the vanishing gradient issue, studies on deep residual networks, ResNets, revealed that residual connections promote ensembling within networks. We propose that, similar to ResNets, residual connections in language models enable gradient descent to create ensembles of relatively shallow computational subnetworks. By doing so, networks avoid heavy reliance on individual paths, thus enhancing their ability to withstand layer-wise interventions. Recent findings on self-repair mechanisms supporting this hypothesis demonstrate the existence of parallel computational paths. We now present our hypothesis on the 4 universal stages of inference in transformer language models. It is important to note that the boundaries between these stages are not rigid, and multiple stages can occur simultaneously. These stages represent general computational patterns, while the processing of specific tokens may involve more personalized dynamics, such as factual recall. In stage 1, known as detokenization, we infer that the first layer in the model acts more as an extension of the embedding rather than a typical layer. This is particularly true for the Pythia model family, where the first MLP layer is influenced solely by the current token due to the use of parallel attention. After computing this extended embedding, the model combines nearby tokens related to the same underlying word or entity to incorporate local context and transform raw token representations into coherent entities. Neurons have been identified to activate for specific sequences of tokens, requiring attention heads to copy nearby previous tokens into the current token's residual stream. Early layer attention heads tend to focus more on nearby tokens than later attention heads, as shown by attention distribution analysis. Moving to stage 2, termed feature engineering, we propose that a specific region of the model engages in constructing features that are valuable for predicting future tokens. This stage involves creating increasingly abstract features, transitioning from shallow syntactic features to richer semantic features. The features generated here significantly impact downstream predictions, as indicated by various experiments on sentiment, truth, and zero-shot function execution. In the subsequent stage, prediction ensembling, stage 3, the model begins translating semantic features into concrete predictions for the next token. This process likely involves ensembling, where multiple subnetworks contribute to the final output through a voting mechanism, leveraging the robustness observed in the model. Furthermore, we identify prediction neurons that promote probabilities and suppression neurons that inhibit predictions, with their distribution changing across layers. Prediction neurons become more prominent towards the latter layers, indicating their crucial role in the prediction process. Section Summary. In this section, we explore why language models are robust to layer-wise interventions. We propose that residual connections in transformer models enable the formation of ensembles of shallow computational subnetworks, reducing reliance on individual paths and increasing resilience to interventions. Additionally, we introduce a hypothesis outlining 4 universal stages of inference in transformer language models, from detokenization to prediction ensembling, supported by evidence from model behavior and feature engineering processes. Section. Change in intermediate prediction. In this section, we examine the changes in intermediate predictions. We analyze how close the model's representation is to the next prediction by looking at the remaining distance in figure. We observe that as the prediction neurons increase, there is a phase transition leading to a decrease in KL divergence. The number of prediction neurons peaks around 85% through the model's layers and then decreases in the final layers. Phi-1 has fewer prediction neurons compared to other Phi models and shows a lower slope in its KL divergence. GPT and Phi models have more prediction neurons and steeper, smoother KL divergence slopes than Pythia. Surprisingly, Microsoft Phi models, known for their superior performance, have nearly 15% prediction neurons per layer and 25% suppression neurons, which is higher compared to GPT-2 and Pythia models. However, around 90% through the model layers, the prediction neuron density decreases as the models approach their final distribution, sometimes even speeding up, indicating the involvement of other mechanisms, possibly the final stage of inference. In the next stage, called residual sharpening, the decrease in prediction neurons suggests the presence of a new member in the ensemble that aids in predicting the next token distribution. We find that the final layers of all models have the highest density of suppression neurons, which may delete previously constructed features, suppress probabilities of invalid tokens, or adjust the confidence in the final prediction. Both prediction and suppression neurons influence the residual stream and can perform each other's functions effectively. These neurons appear in different ratios and densities across the model. By studying the logit lens entropy of the model, we observe that in some models like Pythia, the entropy increases in the final layers, indicating a reduction in overconfident predictions. This suggests that suppression neurons can either suppress tokens or features outside the top one to sharpen the distribution or reduce confidence in the top token to flatten the prediction distribution. This finding aligns with previous research indicating that models may shift towards incorrect tokens in the final layers, and pruning or reducing these layers can enhance performance. The concentration of suppression neurons is highest in the final few layers of the model, surpassing the predictive neurons in quantity. The intensity of this change is measured by the norm of the MLP output, where a larger norm implies a greater impact on the residual. Removing or changing the position of the final layer leads to model breakdown, similar to what is observed in the initial layers where attention norm is highest. This highlights the significance of the ordering in the first and last layers due to the substantial impact they have on the model. To integrate the stages of inference hypothesis with mechanistic descriptions of models, we present two case studies. The first case study focuses on attention heads responsible for constructing multi-token words, known as subjoiner heads. These heads aid in capturing the context of a token for accurate prediction, contributing to detokenization and feature engineering stages. The second case study provides evidence of the collaboration between prediction and suppression neurons. Through probing experiments, we show that multiple prediction and suppression neurons working together outperform individual neurons and sometimes even surpass the model's performance. Section Summary. In this section, we analyze the change in intermediate prediction in neural models. We observe a phase transition in KL divergence corresponding to the rise in prediction neurons, with Microsoft Phi models showing higher densities of prediction and suppression neurons compared to GPT-2 and Pythia models. The final layers of all models exhibit a high density of suppression neurons, potentially aiding in refining predictions by deleting irrelevant features and calibrating confidence levels. Section. Study 2. Predicting the suffix ing. In this section, we explored predicting the suffix ing. We found that neurons working together can make better predictions than a single neuron. To investigate this, we created a dataset with two classes, tokens ending with ing, and those that do not, each with a context of 24 tokens. We trained linear probes on 32 active prediction and suppression neurons, both individually and in groups. The results showed that ensembling of neurons is crucial for accurate next token prediction. Our study suggests that the second half of the model complements the first half. We observed that the model repairs and erases information differently in each half. The first half develops complex representations, while the second half has the ability to refine them. We also noticed a mystery in the final layer of the GPT model, possibly due to tied embedding and unembedding weights affecting attention mechanisms. However, our study has limitations in pinpointing the exact differences between GPT and Pythia models. Future work could focus on addressing these limitations and exploring sparse autoencoders to gather more evidence for our hypotheses. Overall, VL led the study, while WG and MT contributed to the design and analysis, with critical input and revisions from both.